Okay, I'll start off by wishing everyone a good afternoon. And again, thank you so much for joining us for our fifth seminar in this new series. Before starting, I'd like to notify you that we are recording this session. So if you would not like to be shown or to appear, kindly turn your camera off. My name is Zach Conti, and I'm a research associate at the Alan Turing Institute in London, although I'm currently talking to you from my home back in Malta. Hopefully, not for long here. So I'd also like to introduce my colleague, organizers of the seminar series. So there's Andrea Pizzaferrato, who is an assistant professor at the University of Bath, and Temis Patsas, who is also a research associate at the Alan Turing Institute. And for those of you who are not familiar with the Alan Turing Institute, this is UK's National Institute for Data Science and AI. So if any of you are interested in sharing your work in one of the upcoming seminars, Physics Enhanced Machine Learning, then please feel free to get in touch with us. So as for the format of this seminar, our speaker, Maldon, will talk to us for around 30 to 40 minutes, followed by a Q&A session where the questions can be asked in person by raising your hand or directly in the chat. And of course, I can relay these questions. So without further ado, I'd like to ask my colleague Temis to introduce our speaker for today. And with that, I thank you.
Thank you, Zach. Thanks everyone for tuning in. Today's speaker is Maldon Goodridge. He has a bachelor in economics and mathematics from the University of West Indies, campus. Also a Master of Science from the University of Southampton, and he's currently a PhD student at the Queen Mary University of London. His research interests include renewable energy technologies and quantitative modeling. And today he's going to talk to us about rare event sampling. Maldon, you're free to go.
Great, thank you so much. First, I want to express my gratitude and thanks for the opportunity to speak here and to present our work. And in that light, myself, Maldon, along with John Moriarty and Andrea Pizzaferrato, we will have worked on a manuscript entitled A Rare Event Study on Frequency Regulation and Contingency Services from Grid-Scale Batteries, which was recently published in the Royal Society Philosophical Transaction A, June 2021 publication. Now, what is the motivation for our work? Well, our aim is to try to attempt to understand the benefits and risks of grid-scale batteries, or what we will call battery storage energy systems, or BESS, to frequency management in power grids. Now, to understand why this is important, we need to go back a little bit. Traditionally, power systems were relatively simple things to control. In a power system, our aim would be to maintain frequency and voltage stability. And the way the network operator would do this is that the network operator can control energy generation and supply through nuclear power plants, gas and coal power plants. And this would be used to match a fluctuating energy demand, fluctuating but predictable. However, in light of the current climate crisis that we are facing, it has been decided by multiple governments across the world that we need to introduce more renewable energy sources into our grids. And these renewable energy sources can be classified as distributed energy generation, or DEG. These are decentralized energy sources, and they're located on the distribution network, hence the name distributed energy generation. And this is the low voltage network, pretty much where homes and businesses are connected. Now, these normally take the form of solar and wind power. And while they're great for the environment, they're not so easy to manage under traditional grid operation procedures. Their primary problem, or the primary challenge, is the fact that many of these DEGs, especially wind and solar, are prone to intermittent power injections. And these intermittent power injections into the network, either positive power injections, or they may be supporting the network, and then due to exogenous variables, the power they produce immediately stops. In either case, these can cause or induce dangerous power fluctuations, which can threaten voltage and frequency, which we're trying to keep stable. And these can end up causing damage to the equipment or even to personal appliances in homes and in businesses. Okay, so how do we combat this problem of these random power injections from DEG? Well, it's been proposed that very large, fast response batteries may be able to mitigate some of these problems if they're properly placed across the network. So our research, our main aim is to understand the benefit and risk that these large-scale, fast response batteries can have for frequency management. So in this presentation, what I would like to do is to carry you through our thought process of how we built the assumptions and the models for our work. So we'll start off by developing a power system model that captures detailed frequency dynamics, and that's going to include network and generator and load models, protection systems related to frequency stability, battery storage systems, and low inertial renewable energy models. Once we have this power system model, we're then going to develop an uncertainty model for the problem. What's the problem? These random power injections from renewables. Then we're going to discuss the sampling problem. Well, we are going to come across an issue where how do you draw samples in order for us to achieve our aim? And then we're going to go into a case study of the two-area network and discuss the results of that network. So let us begin. The network model. Now, as it might be easily assumed, electrical networks can be mathematically modeled as an undirected graph consisting of a set of nodes which can be partitioned between generator nodes and load nodes. And we're saying that in terms of the generator nodes, there are n of them, so there are n generator nodes. And as the generator nodes, we are talking about the locations of prominent traditional generators, such as nuclear power plants or coal or gas-powered power plants. They can also be loads at these nodes. So for example, the houses close around a nuclear power plant would count as being part of that node. But the dominant feature of that node will be traditional generation. Likewise, in the other part of the graph, you can also have load nodes. And at these nodes, there are no major source of traditional generation. These are the places where you would find cities or communities or households or businesses. Connecting all of these would be a set of edges. And these edges, as you can imagine, which are connecting all the loads and connecting the generators to different degrees, these would be the power lines. So the power lines can be represented as edges on this graph. And the power lines are weighed by a complex variable, Wij, and this is comprised of Pij, which is the unit reactance of the line connecting node I to node J, E, the unit resistance on the line, and L, the particular length of the line. Now, we can summarize how this line performs by effectively understanding how power flows from node I to node J across the line. And this can be summarized in what is known as the B matrix. So this B matrix here, Bij, there's an omega indicator function, but I'll discuss that later. So this Bij function is a Laplacian-like matrix, and it describes how power flows from node I to node J. Now, sorry. Next one. There we go. Now, let's discuss the generator model. So to understand the generator dynamics as a foundation, we're going to start with the third order model for the generator. Okay, well, what is this third order model? Well, it consists of two coupled differential equations. The first one at the top is the swing equation, and this describes the dynamics of this angle delta. And that angle represents the angle of the rotor, the generator's rotor, which is spinning. And that tells me the angle relative to this rotating frame of reference. And the frame of reference is rotating at a speed known as the system frequency. So here in the UK, system frequency is 50 Hertz. In the US and in Australia, it's 60 Hertz. So delta effectively is measuring the angle of the generator's rotor to this rotating frame of reference. So if I take the time derivative of delta, effectively I'm looking at how the generator's rotor is the velocity of the generator's motor relative to the rotating frame of reference. So I can now understand what local frequency is. So while system frequency is arguably what it should be, 60 or 50 hertz, depending on your country, the local frequency of the generator is given by the time derivative of delta plus system frequency. And we need to really take into account that we are measuring the local frequencies for many of the aspects which will come later. All right, so let's take a look into the swing equation to understand at least have a very global view of what's happening in the swing equation. And the swing equation given by M by the second derivative plus the first derivative of delta, right? Well, what are these terms? Well, M is the system inertia. It's the sum of all the inertias of these very large spinning masses across the entire network. And D is the system dampening. Well, what will cause the system to effectively slow down? Well, what's the resistance acting on the system? Well, that's going to be all the loads scattered across the system. All right, well, what's chi-n? Well, chi-n is the generator's mechanical output, and we're seeing that there are two values being taken away from chi-n. Well, chi-l will be any loads located at the generator node, and then there's this summation term, and there's a bit of a hint what that could be. If he's looking at that summation term, you see this Bij factor coming up again. Well, if you remember the previous slide, we said Bij is a summary of the performance of each line. So this summation term is all the power being extracted from the generator via the lines connected to that generator. So we can understand in principle what's happening to the dynamics of the particular machine. For each machine, it is being supported by the mechanical power being produced by that machine. And what is being taken out? Well, all of the active power being consumed by the loads and all the power being transmitted across the power lines connected to that generator. So we can build an intuition. If it is that the mechanical power is greater than what's being extracted by loads or by power lines is more. So if the generator is producing more mechanical power, the generator is going to accelerate. And that makes sense, right? And the opposite is also true. Okay, so now we have an intuition for the swing equation and how it relates to power system networks. What's the second equation? Well, the second equation gives us dynamics for the voltage, the internal voltage of the generator. But why do we need that? We're more concerned with the frequency dynamics. Well, we want to apply a power disturbance at time equals 0, and we want to understand how frequency varies according for a period of about 15 seconds for our simulations. Power systems theory would tell us that if we only try to model frequency deviations using the swing equation, that solution is only valid for about 1 second. Our simulations are longer. And to have a better picture of what's really happening to frequency over longer transient periods, we need to also include any dynamics or coupled dynamics coming from changes in the voltage. Hence why the third order model is the swing equation plus the voltage equation. All right. So how do we model loads? We just spent a few minutes discussing generator modeling, but what about loads? Well, loads are modeled dynamically as motors. In many ways that you can model a load in power systems, you can model them statically and include them in that Bij in the lines. But we actually thought for our purposes, and you'll see why later on, it's important for us for loads to be dynamic and changeable within the actual simulation. So loads, they consume active power and they require the imputation of electrical power from any lines being connected. For all networks that we will investigate, and for our case study, we are going to model that loads are located at every single node in the network because this seems reasonable and realistic to us. Okay, so this is the basic of the third order model for the generator. We have the swing equation describing frequency, and we have the voltage equation describing the variations in internal voltage at each generator or each machine. We also have it now for the load. So what's the equilibrium state of this system? Well, at equilibrium, all machines are spinning with system frequency. So that means that the time derivative of delta for any motor or any generator, that should be 0. That implies that the total active power being generated in the entire network is equal to the total active power being consumed in the network. We've reached an equilibrium state. And since active power is equal to the active power consumed is equal to what is being generated, there is no force, there's no additional force acting on the rotors, so therefore there is no acceleration in any of the machines in the network. So that's our equilibrium state, and that will be the state in which we start all of our simulations. So now that we have this basic third order model, there's still other factors which can affect frequency. And these factors are known as frequency regulation and frequency protection systems. So regulators monitor the frequency or the voltage and adjust the generator's performance in real time to return the system back to equilibrium. Remember the overall picture? To make sure the system remains stable, we have to keep voltage and frequency stable. So we have these real-time systems which are measuring voltage and frequency in real time and adjusting the generator's output in real time to maintain equilibrium. Over frequency, we have something called the generator's governor. Well, what's that do? That measures the local frequency at the generator, and it adjusts the generator's power output to counter any variation in local frequency. Well, how do we model this? Well, this is an additional dynamic dynamic term in the generator model that's enclosed in green. And the one subscript W for the time derivative of delta is an indicator function, which equals 0 when the local generator speed exceeds what we call the governor deadband. Within this deadband, the governor will not command the generator to make any responses. This would be to avoid unnecessary oscillations or excessive oscillations. But once the local speed of the generator exceeds the governor's deadband range, then the governor will command the generator to increase power if the frequency dips too low, or if the frequency goes too high, it will command the generator to slow down. Now, a second regulator which we model is the automatic voltage regulator, the AVR. This very similarly measures local voltage, and if it deviates from expected norms, then it's going to alter what's called the excitation of the generator through a transfer function. This is modeled through a transfer function. But how does that impact on our equations? Well, that impacts on our equation by changing in the orange circle, is changing this EI factor with this epsilon factor. The epsilon factor is the AVR correction. So what's the intuition for this? Well, the generator is responsible for producing active power, which maintains frequency, but it's also responsible for producing reactive power, which maintains voltage stability. However, the generator has a capability curve. It can only produce a limited combination of reactive and active power. So if there is a sufficiently severe voltage threat, the AVR may command the generator to produce more reactive power, requiring a reduction or a change overall in the active power output. That can have an impact on frequency. And remember our aim is to build as complete a picture as we can reasonably of voltage, of frequency dynamics, so we can understand how batteries can affect this. So the AVR can have effects on the excitation of the generator, which can have a ripple-on effect on the speed at which the generator is turning and thus its frequency. So we model these regulation services. In addition, we also model emergency systems. So what's an emergency response scheme? How is that different from a regulation scheme? Well, in an emergency response scheme, we're really talking about disconnecting components of the network so to protect other components or so to protect them. So there are two types of emergency responses. We have generator emergency responses, which will disconnect a generator from the network if certain parameters are met. We modeled two particular forms of generator emergency responses, something called rate of change of frequency protection. Pretty simple to understand. Again, there's a sensor by each generator monitoring Markov, or the second derivative of the phase angles. And what's going to end up happening is if this reaches a particular threshold and holds for too long, the cyber model that we've developed will disconnect the generator from the network. Likewise, over frequency generation shedding does a very similar thing. It's monitoring the frequency. And if the local frequency exceeds a particular threshold, it's going to disconnect the generator from the network. Okay, so how do we model this? Well, in simulations, once any of these criteria would have been met, the simulation is paused, and then we change the structure of the network to match. So this stylized theta value, as highlighted in the different models, we can understand which factors are being affected by these generators being disconnected. So first we can see that the system inertia is affected by the loss of a generator. Well, that makes sense. If the generator is disconnected and the system inertia is the sum of all the present inertia of machines there, then before the generator, we have to adjust the system inertia. Likewise, chi n, which is the mechanical power being produced by a particular generator, if a generator is disconnected, that has to be adjusted and set equal to 0 for the particular generator. Again, excitation. The excitation is associated with the generator. If we lose a generator, we lose this excitation. Now, and the final emergency scheme that we model would be network emergency schemes. Well, these do not directly disconnect a generator, but in fact, they disconnect other components of the network graph. So the first one is under frequency load shedding. So what happens in under frequency load shedding? Again, across the entire network, we are modeling or we are sampling frequency. If frequency falls progressively to any of these particular thresholds, we initiate a 10% shedding of the pre-contingency load at that point. So under frequency load shedding is a progressive scheme which, in response to reductions in expected or desired frequency, it will shed 10% of load at that particular node in a hope to arrest the fall or to arrest the decline in frequency at that particular area. Likewise, the interconnector trip will disconnect any line when it detects that there's excessive power flow across that line. So again, how do we represent that in the model? Very similar to how we represent a loss of a generator. Once any of these parameters are detected, we will pause the simulation and we are going to adjust the structure of the model. So what is affected by under frequency load shedding? Well, for sure, chi L. We're going to lose loads at that particular node where under frequency load shedding has occurred. But the damping, system damping is going to change. Remember, system damping is a function of the loads. So if we lose loads, we lose a bit of damping as well. Well, how do you model the loss of the line? Well, the loss of the line is modeled by the adjustment of this susceptance matrix, this BAJ matrix. So if you look within the sum terms, we see that the susceptance matrix is also highlighted. And when we lose a line, the value for that line in the BAJ matrix is set equal to 0. Hence, that's the purpose of the omega factor. So the omega factor is an indicator which sets, which has a value of 0 whenever a line trip occurs. That means no more power can flow across that line, and effectively you remove that line from the graph. Okay, so very quick consolidation of thoughts. Where are we? Well, we have a model for the generator, a basic model, the third order model. And now we have protection systems, both regulatory, the AVR and the governor, and emergency responses. Over frequency generation shedding. We also have under frequency load shedding, the loss of the interconnector line, and now we also have a model for a rate of change of frequency. So we can lose generators, we can lose lines, and we can lose loads. Now, how do we model the battery? Well, fast-acting grid-scale batteries are deployed on the network, and we're going to deploy them at strictly pure load nodes and not to go at generator nodes. Well, why is that? Well, simulations and literature from power systems engineering would dictate that it is best to, for maximum effectiveness, it is best to place these large grid-scale batteries at the locations relatively far away from generation sites. At a generator node, there's already a generator there being supported by a governor. At load nodes, they're the ones most susceptible to changes in frequency. So it is most prudent to place batteries at pure load nodes where they can offer the maximum support to the system. As I said, this is backed up both by our simulations and by literature. Batteries are modeled to operate in 3 distinct phases as shown in the graph. So the first phase is what is known as the deadband operation. we do not assume that at the start of our simulations that batteries are in an inactive state. In fact, we assume that the battery is already in some pre-contingency or pre-simulation state. It can either be discharging or it can be in a charging state. This is the P01 or P02. During deadband operation, when frequency deviations are relatively small, the battery will continue its pre-contingency operation. Number 2, regulation, frequency control, ancillary services, FCAS. In this operation mode, when frequency is between FD and FN, the battery is going to respond to the automatic generation control unit. Now, the AGC is going to send regular, discrete, intermittent signals to the battery, which allows the AGC to coordinate a system response to frequency deviations. How does that work? Well, sensors across the entire network will sample local frequencies and then take an average. And this will allow it to calculate an average frequency. This average frequency is then communicated to the batteries, and the batteries will then respond to the average frequency in order to maintain equilibrium. The battery will maintain this commanded output until the next AGC signal, and we model AGC signals to come approximately every 15 seconds. Well, what's the last mode? The final mode of operation is local contingency operation. The battery responds with its full capabilities in response to excessive frequency deviations at its local site. In this particular operation, this is between FN and FM. The battery is going to ramp up or ramp down as much as necessary to bring local frequency back within nominal operating bands. It will ignore any AGC signals during this time. Once the frequency has returned to nominal operating band, the battery will then return to the AGC signal when it is next received. So that's our model for the battery. Okay. So our final model to complete this picture would be, well, how do you model distributed energy generation? Well, we attempt to model a network with high penetrations of low inertial DEG, right? And we're going to apply this to every single node in the network, right? Why? Because renewable sources can be found almost anywhere, even in houses next to the power plant. They may have solar panels or a small wind turbine in their backyard. So how do you actually model it? How do you include it into our model that we're building right now? Well, renewable power inputs are modeled as random fluctuations of loads at each node. So this means, we are associating renewables or renewable generation with the loads for the same reason. The renewable energy sources, whether they be solar panels or wind turbines, are usually located on homes or commercial enterprises. So to understand how distributed energy generation can be modeled, then it may be best to model this as a part of the load. So at equilibrium, the load figure that you see is actually a combination of the actual load subtracting, and from that we subtract the renewable energy generation that's supporting it. Now, how do distributed energy generation contribute to system inertia? Well, they don't. If you think about how a solar panel works, it's not a big mass that's spinning, that even if you remove the mechanical power, like you would in a regular generator, it would take time to slow down. No, once a cloud comes over a solar panel, it will immediately stop producing power. So there's very little inertia to the change in power output from these systems. And that actually contributes to the difficulty in their management. So now that we understand how we built this power system model, how do we actually model the problem? I remember what the original problem was. The original problem was random power inputs coming from DEG. So we need an uncertainty model to describe it. Well, let's define a power disturbance now officially. So a power disturbance is a vector U applied to all nodes in the network. Remember we said there are n plus L nodes in the network. It's a random change in the load at each node due to, for instance, errors in renewable generation forecasts coming from weather, etc. They're applied again to all nodes as impulses at time equals 0 in our simulations. And once they're applied, entire simulation. Now, our simulations could also have adopted a variable power disturbance, but we think to best understand how batteries can mitigate the problems coming from these random power disturbance, we kept them constant. Now, each power disturbance then is calculated as a proportional change to the stationary initial load. So you take the stationary initial load, chi L, and you multiply it by this U, the vector of random power disturbances, and that tells me the power impact that it actually has in the network. And you can actually see that in the model above. So power disturbances then create transients in the frequency dynamics. Once they've been applied to the network at time equals 0, frequency is going to oscillate, and we are interested in, well, once frequency oscillates, what are the consequences following that? Now, we're really interested in understanding how the relationship between disturbances across the network can affect, can be mitigated and can affect battery performance. So if you really think about what the underlying mechanisms for what we say power disturbances, the power disturbance occurs when these DEG power sources are affected by exogenous variables such as weather. So conceptually, you can imagine that you have a solar panel and then suddenly there's a cloud over that solar panel, and it's an unexpected cloud. We didn't expect it to go cloudy just yet. So the power system is depending on the power coming from the solar panel, and then all of a sudden it disappears. But that's not only going to affect one solar panel, it's going to affect multiple solar panels across a wide area of the network. So more scientifically, random power disturbances induced by weather will not be a local phenomenon. It will actually end up affecting large areas of the network. And this implies that weather-induced power disturbances can result in correlated disturbances across the network. So to reflect this, we model our disturbance vector U as a zero mean Gaussian with a covariance matrix sigma parameterized by two variables, sigma and alpha, where sigma tells us the diagonal value of the covariance matrix, which we just know as variance, and the variance can be seen as modeling how rare large events would be. For a large variance, then large disturbances will be less rare, and vice versa. Well, what about alpha? Well, the off-diagonal values of the covariance matrix is given by alpha times sigma squared, where alpha is in the range 0 to 1 to ensure that that is a functional covariance matrix. But we can also interpret the values of this alpha. An alpha of 0 implies that the disturbances across the network have no correlation, that is, they're independent events. While an alpha of 1 implies that they're almost perfect, well, not almost, that they are perfectly correlated. So our aim is to understand how batteries are affected by correlations in these power disturbances. Now, we do have some additional uncertainties. Now, remember, a few slides back, we did say that the pre-contingency state of the battery, we don't assume the battery is in an idle state when the simulation begins. It's in some pre-contingency state. So how do we select the pre-contingency state? Well, we sample it. The literature has said that for batteries, batteries, when responding to frequency regulation services, it must ensure that at least 50% of the battery is available for emergency responses. So we decided that the initial state of the battery can be sampled uniformly from a 50% charging state to a 50% discharging state. Or in other words, take the maximum power of the battery and divide it by 2, and we're going to take that, we're going to sample the initial power of the battery uniformly from a negative value of half of, right, sorry about that, to charging up to half of its power output. Now, again, to stress, this is to ensure the battery has at least 50% of its capability and power to respond to any local emergencies. Now, A second uncertainty that we attempted to model, we did not assume that that time equals 0 for our simulation corresponds to the instant an agency signal will be received by the battery. Or put another way, the time equals 0 at the beginning of our simulations can occur at any point in the interval between AGC signals. So to reflect this, we modeled the first AGC signal to come in at approximately, we model that to be a uniform random variable. So we uniformly sample the time until the first AGC signal in our simulations, and then the AGC signals will come in intermittently and discretely after that. All right. So we just did a very big summary of the engineering modeling for our paper. So it's good to actually remind ourselves of what the research question is. In networks with high penetration of renewable energy sources, we want to understand the benefits of BESS, of battery energy storage systems. If that is the case, we actually designed 2 experiments to help us to understand that, based on the 2 major characteristics and functional features of batteries. The first one, batteries can benefit regulation services. So we have an open question. How well do batteries mitigate excursions in frequency beyond the normal operating frequency band, right, following power disturbance from DEG? And the second experiment, the second question we want to answer, but how well do batteries mitigate load shedding events resulting from random power disturbances from DEG? So how do we approach this problem? Well, let's apply batteries with varying maximum power outputs, MPOs, to the power system that we discussed. And then let's draw samples from this parameter space of the uncertainty of the random variables that we're interested in, conditioned on the occurrence of a frequency instability event. Well, that's a conditional distribution. So we want to sample from a conditional distribution. If I can understand how the disturbances, if I can understand the relationship between disturbances, given that a frequency instability event has occurred, I can then set limitations on what the batteries can and can't do. So, well, what's a frequency instability event? Well, that depends on the experiment. For frequency regulation services, a frequency instability event would be frequency going beyond nominal operating band. Well, what about for contingency management? Well, the frequency instability event that we would condition on would be the occurrence of at least one load shedding event somewhere in the network. So if I condition for these events and then record the disturbances associated with these events, or given that these events have occurred, I will understand the limitations of what the battery can or cannot do. But there's a problem. Sampling from this conditional distribution is going to be challenging. Even without large batteries, frequency instabilities, as described before, are already classified as very rare events. So if we think about it, here in the UK, there was only one such event recorded in the past 2 years by the National Grid, and that's the infamous August 2019 event. Secondly, as battery MPO increases, larger disturbances are required to trigger whichever kind of frequency instability we discussed. But remember, disturbances are modeled as a zero mean Gaussian, which means larger disturbances imply that they're becoming more rare. Point number 3, as the number of locations of renewable energy sources increases, so too does the dimensionality of the problem. Let's pause there. Points 1, 2, and 3 imply that we're trying to sample from the tail of a distribution. Well, what's the most common sampling technique that we have? Well, Monte Carlo sampling. The first 3 points already implies to us that in an attempt to draw IID samples from what is the tail of a distribution is going to take an extraordinarily long time. You have to draw a lot of samples in order to get a representative, you have to draw a lot of elements in order to get a representative sample. So we already know from points 1, 2, and 3 that Monte Carlo sampling is going to be highly inefficient for this purpose. Okay, well, there are other alternatives. We can try Markov Chain Monte Carlo sampling. You can use a random walk. You can use Gibbs sampling. We have other options. But then point number 4 challenges these. So the support of this conditional distribution that we're interested in, remember, these are really parameters given that frequency instability event has occurred. They're expected to be well separated by large subsets of parameters which don't lead to frequency instabilities. And we can imagine that in this case, well, what kind of disturbance at a node will lead to an instability? It will either have to be a very large positive disturbance, meaning a large power injection, which can cause a frequency instability, or you would need to have a large amount of power being taken away, a negative power disturbance, a large magnitude negative power disturbance. But that means that there's a wide range of power disturbances close to 0 where you wouldn't have any frequency instability. So that means the support of the distribution that we're interested in sampling is separated. And this is a challenge for MCMC techniques. But let's see why. So, well, what's MCMC, right? So MCMC, we know is a technique where we can separate sampling. We can sample from a target distribution by selecting a general proposal distribution, which allows us to propose a new particular point, and then we can pass that point into an acceptance density, which determines whether or not to accept that position. So suppose you have a parameter space omega, and that can be partitioned into 2 regions, C and not C. And we desire to only have samples from C. So let's define our target distribution pi as a conditional distribution, right? We only want samples from my region C. And the way that, if C is not convex, if it is that, if there is a large region of not C in between the regions that I'm interested in, traditional Markov Chain Monte Carlo algorithms, they're going to get trapped in the regions of what we call local maxima, right? And as you can see the graph to the right, that's what would have happened here. The region C, in this case, would be x and y, and the absolute value of x minus y greater than 5. And this creates 2 regions of C in yellow that I'm interested in sampling from. And if I initiate sampling from the point 1, 9, that's in the upper left-hand portion, if I run an MCMC algorithm, it's going to be very difficult for us to get out of that region and sample the second region, the second yellow region, to the bottom right. Now, I could increase my proposal variance. I can try to jump further. But remember, one of the key characteristics of MCMC sampling is that you want to keep the acceptance rate around 25%, and that's controlled by your variance. So your variance, your proposal variance, is really dedicated to make sure that you have this 20 to 23% acceptance ratio to ensure that you're properly exploring the region. So this constrains MCMC sampling from sampling these disjoint supported regions. So where does that leave us? We can't use Monte Carlo because we are doing tail distribution. We're trying to sample from the tail of the distribution. And traditional MCMC is difficult because the support is separated and we're not going to capture the entire region that I'm interested in. So John Moriarty, among others, would have developed this sampling methodology known as the skipping sampler. And what the skipping sampler is going to do is that it allows us to update the proposal instead of simply rejecting it. So let's go through a sequence. Let's say the chain starts at the position xn, that's within C. The algorithm is then going to make an initial proposal, just like it would in a regular MCMC. Now, if this original proposal, I'm going to call it Z1, is in my region that I am not interested in, based on how we've constructed our target distribution, that should automatically be rejected. It's not the region I'm interested in, reject it outright. However, to prevent this from happening, the way that the skipping sampler is going to work is that if the point Z1 is not in my desired support, then I'm going to take the direction of Z1 from X to Z1, I'm going to call that phi, that's my direction. And I'm going to sample a number of distance increments called R. So I'm going to sample a jump distance. And then I'm going to propose, well, how? Well, simply take Z1 and add R times the distance multiplied by the vector of the direction. So that means I'm going to be, my Z2 is going to be in a straight line displacement from X to Z1 to Z2. And then I test again, is Z2 in the region, in the support that I'm interested in? If it's not, we're going to sample another independent distant increment, and we're then going to propose Z3. So what are we doing? Conceptually, you can imagine it as skipping a stone over water, or skipping a stone between a river. You want your stone to land on the land, so instead of you just tossing the stone into the water and it's sinking, you skip it over the water such that it lands on the land on the other side, on the bank of the river on the other side. This is the motivation for the name, the skipping sampler. So how does this address the original issue of traditional MCMC sampling? Easy. In traditional MCMC sampling, the point Z1 would have automatically been rejected, returning you to X and forcing you to sample from somewhere else. And because of that, you would never have been able to escape that upper left-hand yellow region. But by the skipping sampler allows us to update the proposal without necessarily rejecting it. And that allows us to improve our exploration of our desired domain. This improved exploration then allows the chain to transition between the different components of the set C that I'm interested in. It allows us to transition between disjoint support for our distribution. That overcomes the original issue of MCMC sampling, and it allows us to draw samples efficiently, as we can see from the top right graph, where I tried the same problem, but now with the skipping sampler, I can see that we have samples in both regions. So we now have a methodology that can, it has the benefit of MCMC for sampling these tail events, but it overcomes the disadvantage of MCMC by allowing us to sample from these disjoint support systems. So what's the case study and what are the results? So the case study for our results, we applied the skipping sampler to sample these power disturbances. Simulations were conducted for a variance of 0.003 to ensure that they are sufficiently rare. And then we conduct simulations for various levels of the correlation factor alpha, 0, 0.2, up to 0.8. We allow the chain to skip. So we conduct 10 to the 5 proposals for the skipping sampler, and we allow it to update a maximum of 15 times. If after 15 times it does not find a location that's within our set C, then we return back to the original position. And we define our set C to the subset of disturbances which result in the frequency instability. We apply this to the Condor 2 area network. And our experiments last for approximately 10 seconds, and we record any frequency instability metric, and then we finally record the disturbance vector U associated with that instability metric. The Condor 2 area network has 14 buses, but we can use this engineering technique where we can reduce the number of buses from 14 down to the critical 6. 4 generators and 2 load nodes, and their batteries located at both load nodes. I'll go further to say that the area is separated into 2 areas. So we have generators 1 and 2 and load 5. That's area 1, and area 2, load 6, generator 3 and generator 4. So what results have we found in our simulations? Well, first, we found that the battery can be used to prevent, for our frequency regulation services, the battery can be used to minimize this metric called the frequency excursion area. So when the frequency excursion area is simply the area that the time series of the frequency frequency plot would have exceeded the nominal operating band as shown here in green. And according to these results, there are three figures here. The figure to the left is measuring this thing called the FEA, this frequency excursion area, how much time the frequency time plus spent outside of the nominal frequency band. And as I expected, on the x-axis, we're seeing the battery's maximum power output. As the battery MPO increases, the FEA decreases. And it's not a linear decrease. It is actually the bulk of the benefit of the batteries comes pretty early on. So for relatively small battery sizes, up to about 400 megawatts, we're seeing a rapid reduction in the frequency excursion area. We can interpret this as an increase in the battery's maximum power output has the effect of reducing the severity of frequency excursion events. The second graph is showing us that as the battery maximum power increases, the disturbances conditioned on a FEA event occurring, that's actually increasing, which makes sense. It requires larger and larger disturbances in terms of magnitude to trigger FEA, whereas the battery size increases. But another conceptual way of looking at it would be, remember, these disturbances are modeled as a zero mean Gaussian. Larger disturbances imply rarer events. So let's combine it all together into a coherent story. Increased battery power reduces the likelihood of the FEA event, and it also reduces its severity when it does occur. Okay, but what about the second experiment? In our second experiment, we wanted to understand, well, how do battery storage systems impact on contingency services? How does it prevent load shedding events? So let's look at that. Let's use the number of load shedding events, the average number of load shedding events as our metric. The graph on the left shows us that initially, the severity of load shedding events seems pretty stable for all of the different values of alpha for different correlation values. However, as this increases, as the battery power increases, the severity of load sheds or the number of load sheds decreases rapidly. Well, let's look at the second graph. The second graph, in the spirit of the first one, is showing us that in the initial period corresponding to the first graph, the disturbances required to trigger a load shedding event are increasing rapidly, which means that batteries, relatively small scale batteries, are making load shedding events more rare. It's reducing the likelihood of load shedding events occurring. That's great. But as the battery MPO continues to increase, we actually see that the occurrence of these load shedding events increases as the magnitude decreases. So there seems to be this very complicated relationship occurring between these larger battery sizes and greater instability in the network. So to understand that, we did a little bit more analysis of the two-area network, and we understood what was happening. For highly correlated disturbances, the battery locations at load number 5 and load number 6 results in excessive power being pushed from the battery in area 1 to area 2, causing the line to trip. When that line trips, it results in exacerbating the instability already present in the network, causing a cascade of other failures such as Markov and overfrequency generation shedding. Finally, we'll take a look at, is there a conflict between the batteries operating for frequency regulation and for contingency services? Well, yes, there is. For very large batteries, if they are allowed to use up to 50% of their power output just to regulate frequency, then you are putting the system in a precarious position where a correlated disturbance, or so a disturbance with the same sign as the state of the battery, may overwhelm the system and cause the system to end up becoming destabilized, causing a load shed. So our results show that there was a correlation between the initial state of the battery and the disturbances which resulted in a load shed for very large batteries. And this makes sense that if the battery is already outputting, let's say, 500 megawatts onto the system, and then you have a large disturbance which adds another 100 megawatts onto the system, the battery may not be able to respond fast enough given the correlation between the two. So that can then end up with too much power being pushed through the interconnector line, resulting in a line trip and a cascade of failures. So we can conclude that batteries have a significant potential to regulate frequency in modern grids with high penetration of DG. They reduce the severity and the likelihood of frequency excursion events. Batteries also reduce the likelihood of load shedding events for small to moderate battery outputs. But large battery outputs can destabilize multi-area networks as it pushes too much power through the very few lines that make up interconnectors. Lastly, battery energy storage systems with very large maximum power outputs should reduce the proportion of power available for frequency regulation. Otherwise, correlated disturbances can actually induce significant disruptions in the network, resulting in greater instability. So I think that brings me to the current end of my discussion and the presentation of the work in our paper. And I will now open the floor to you if there are any questions.
Thank you very much, Maldon, for that very comprehensive presentation. We do have we're a little bit over time, so maybe we have time for one pressing question from the audience. And you can do so by either typing it in the chat function or by asking it in person.
Yes, Zach, can I ask a question?
Of course.
Yeah, thanks. I think that was a great talk. One question I have is, how does the location of where the battery is installed affect, affect the mitigating effects of the battery, right? Because the power balance equations may imply that even if the battery is present and it has the charge, you may not be able to transport that energy from one point to the other point, because as you know, in a power grid, you always need to satisfy the power balance equations. So I'm wondering, in your simulations, where exactly did you place the battery, and how does the location of the battery itself affect its ability to mitigate frequency violations?
Okay, sure. That's an excellent question. So I'm just going to tap the slide. If you take a look at the two-area network, the batteries would have been located on either end of the interconnector line, so at load 5 and load number 6. So the reason that they were placed there would have been us following the theory or the general consensus in the engineering community that placing the batteries at sites of very large loads tends to offer the greatest benefit. And in the two-area network, the largest loads are now located at load 5 and load 6. To your second question, how does that impact on their performance? So I can briefly describe the results of our simulations. We had placed the batteries at the generator nodes originally. This was before we had any engineering insight. And the results were markedly worse. What ended up happening is that once the battery MPO reached a particular threshold, combined with the action of the generators, you saw many more rate of change of frequency failures and a large number of over frequency generation failures. So on one hand, there is an intuition that yes, placing the batteries at these load nodes is superior to placing them by the generators. There's a caveat, however. The caveat is that in this particular network, the primary loads are located on either end of the interconnector line. And by design, the interconnector line of the two-area network is considered weak by Condor himself. So one of the consequences of having very large batteries on either side of this weak interconnector line, and the fact that they're so fast acting, is that in terms of when a disturbance would occur, especially a power loss occurrence in area 2, the battery in area 1 would very rapidly send power over, or attempt to send power over the line, resulting in that line being tripped. So there seems to be a really interesting balancing act that electrical engineers are going to have to play between supporting loads and having batteries located away from generators so effectively they can help to support the system, while at the same time ensuring that the maximum battery output, its ramp up and ramp down rates are within the tolerance of any weak lines that may exist close around it. Hopefully that answered your question.
Yeah, thank you.
Yeah, you're welcome, sir.
Thank you so much for your question. All right, unless there's any other question. All right, thank you so much, Maldon, for your time and for sharing your work with us. And to the audience, look out for our next seminar. And we will, of course, send this to you in an advertisement email in the coming weeks. So thanks again, and thank you all for attending today.
Thank you. Thank you all.
Bye.
Maldon, bye.